Welcome to Spring LIB.
Alrighty, so we got a truck that's going down the road driving. And just to quickly sketch it out really, really poorly and quickly, this is my lovely truck. My little truck bed back here. And there's the end of my truck. Okay, cool. And then I got a little boy back here chilling in the back of the truck bed, hanging out here. And he goes and he throws an object upward from where he's sitting in the back of the truck. Okay, and so essentially when he does this, the object goes upward, and as the truck continues down the road, the object lands back where the boy is standing. And we know that the truck is moving at a velocity of 9.5. I'm going to say velocity of truck equals 9.5 meters per second. All right, so that's also the velocity of the boy because he's in the truck. So if I wanted to, I could even say this is velocity of the boy, v sub b, but we're just going to call it v sub t, velocity of the truck. First part of the question is asking us, at what angle exactly is he throwing up the ball? Or whatever the object is. What's the angle that he's throwing it up? And if you think about it, he's in the truck, and this is all in the frame of reference from the truck. So for the boy, he's looking at this object go directly up in the air. He continues down the road, and the object is staying at the same velocity in the horizontal direction as a truck. So it's going to look like he's throwing it just directly upward from his frame of reference. So it's exactly 0 degrees. I can put this as part A, 0 degrees with respect to vertical. That's what that's WRT is, with respect to vertical. That's how it's going to look for him. Now, what about the initial velocity throwing up the ball? If you think about it, he is, I want to do this down here, part B. So he's throwing the ball up only in the Y direction, right? So let's go ahead and use, and he think about it as well. Let's actually, before I wait for it, let's write down the equation here that I think would be useful for us to use. So we're going to use this equation here. Now the delta y, think about it. The ball starts at the bottom here, and then once the truck moves the distance, it shows up at that same height later on. So this delta y is 0 minus, it's 0 minus 0 essentially. There's going to be nothing here. It's just 0, conveniently for us. So we'll go ahead and we can continue my work down here. 0 for that y, or that delta y. And then my v naught sub y, that's what we're looking for. So we're just going to leave that alone right now. V naught sub y and times t. Well, we're going to need to figure that out, which we'll figure out in a second, a technique to find that. And then, of course, the acceleration here in the y direction is gravity. So I pulled a negative. It's a minus g because it's going downward while the motion of the ball is initially going upward. So we're going to call that a minus g. It's working against us. So I pulled a negative out, minus g. And we have the t here, again, squared. We can go ahead and keep solving this. And you have t's. If you actually move this to the other side, so real quickly, if I just rewrite this, we now have it. By moving this to the other side, you cleared the negative. And I just put this guy on this side of the equation. Cool. And go ahead and cancel out 1t from both sides. And now we got v naught y equals 1/2 gt. Issue is, how do we find t? We need to know the time of flight here, essentially. How long is this good object in the air for? So let's do that over here. So t, taking a little break. This is really important here. I'm going to start this equation. We'll go back to it in a second. But t, time, how can we do this? Well, we know how far down the road the object lands, essentially. He throws it up from his hand, and 16 meters longer down the road, it lands back in the truck bed. So we're going to call that length it travels L. And we're going to put the velocity of the truck down here in the denominator. This is a simple velocity times time. If I were to put this over on this side, velocity times time equals some sort of length. And the units work out perfectly, as I'll show you guys in a moment. This is one of the first kinematic equations you learn for a constant velocity problem. So we know this information here. The length is given to us at 16 meters. And the velocity of the truck is given, we know that's 9.5 meters per second. Cool. Meters cancels, and your seconds goes back to the numerator here. And when you work this out, we get time equals 1.68 seconds. Now, we can go back to this equation here that I started a moment ago. We're going to take this, I'm going to put it right here and continue for a second. So the v naught y, which is what we're trying to find here, this initial velocity, which is all in the y direction, as we discussed earlier. Now we have everything we need. We have our 1/2. G, obviously, we know we're going to be using 9.81 for that, so I'm just going to leave G in as the variable because it's just a constant that we're going to plug into the calculator. And then, of course, time, just 1.68 seconds. So 1.68 seconds that we just found a moment earlier using our constant velocity kinematic equation. And then once you run through this math, you get v naught y equals 8.24 meters per second. I'm going to box this in. That's our, I believe, our second answer, part B. All right. Now, part C is asking us, I can actually fit this down here because it's a very short part, but it's going to look like, what's the path look like of the object from the perspective of the guy on the truck? And since he throws it directly upward, the trajectory from his perspective is going to look like just a straight line, a one-dimensional trajectory, just up and then back down, all in one dimension. So we'll say vertical trajectory. Awesome. And then part D is asking us a little bit of a different situation. I can actually squeeze this down as well. Squeeze it down here. Now, what about from somebody who's outside of the truck? Maybe I'm on the side of the road and I'm watching this this truck, drive past me at 9.5 meters per second, and I see this object fly up from the truck, and I'm like, whoa! And I see it come out, and then I see it stay just perfectly above the truck as it's already moving, and then I see it land back in the truck bed. So from my perspective, since the truck proceeded down the road 16 meters and I'm not moving with the truck, it looked like a parabolic motion to me. It looked like a parabola. Parabola. Let's say parabola trajectory. Parabolic, parabola, whatever. And that's simply just a trajectory that would look something like this. Our typical projectile motion trajectory that you see. All right, so and the last part is asking us, for that situation, what is the initial velocity? So from my perspective outside the truck, how does it look? What's the initial velocity? So we'll go ahead and we'll just find the magnitude of that, the velocity. We already know the velocity in the y direction because we found that right here. So we just need to figure out the velocities in the x direction, and we just recall the fact that this is, at the end of the day, a projectile motion problem, and the velocity in the x direction will not change, and that's the velocity of the truck. So we actually have both velocities that we need to solve for this, a initial velocity using just finding the magnitude. This guy, using just this is essentially the Pythagorean theorem here to find the magnitude. So the v naught x is actually this v sub t here, and the v naught y is what we have here. So we'll go run through this and plug in what we know. V naught x being the 9.5 squared, and the v naught y being this 8.24 squared. All right, and then you go ahead and throw that in the calculator and take that root, and you're looking at an initial velocity of roughly 12.58 meters per second. And of course, if you wanted to, you could also write this in component form, and you'd have just 9.5 meters per second in the x direction, and 8.24 meters per second in the y direction, or a magnitude of 12.58 meters per second.